All right, so today we're going to take a look at section 3.3. We're going to start it, and we're going to look at increasing and decreasing functions. And we won't get to the first derivative test. Well, we won't get to a lot of applications of it today, but we will talk about what the first derivative test says. All right, so first of all, graph being increasing and decreasing. So we'll draw some pictures as well. But for starters, a graph is increasing when on an interval, a function has the condition that if x1 is less than x2, f of x1 is less than f of x2. And we'll draw a picture. It doesn't have to be inside of the first quadrant, but there's no reason I can not draw it there too. So if it says x1 is less than x2, it means that they are sort of in order on the number line, on the x number line. And what it's telling us is that whatever the f of x1 is, we'll put it here, it's below f of x2. So something like this is going on, and somehow they're connected in between. Okay, increasing, of course, just means that it's going uphill if you read the graph from left to right, which is how we read graphs. It's everything you would expect to be true. Okay, we're going to look at it from a calculus perspective in a moment, but this is just definitions. Decreasing, we still have x1 coming before x2 on the number line, all right? But the f of x1 is actually greater than f of x2. So on my number line, I still have x1 and then x2 like this. But what I need instead is I need the f of x1 to be higher than the f of x2. So I have this point followed by this point somehow, and it's going downhill. Okay, so every now and then I have somebody say, shouldn't the x1 and the x2 be switched as well? If we switched them both, it would still be going uphill. So we have to hold one of them steady. x1 and x2's relationship stays steady, and it's the y's relationship, f of x and f of x1 and f of x2 that swap. Okay, so this is like, I teach this in college algebra. This is not something new, right? You've seen some version of this before. Maybe not the written out pieces, but you've certainly seen graphs talking about increasing and decreasing before. The parts that are new have to do with how this applies to calculus. So let's take a look at that. So it says, suppose that f is continuous on the interval I, and we have a positive derivative. Now remember, derivatives mean slopes of tangent lines. So if the slope is positive, right, if you have positive slope, it means that you have a graph that looks like this, right? It's an increasing graph. And that's what this is saying, even if you aren't talking about lines. So if the derivative is positive, then the graph is increasing. And by the same token, if the derivative is negative, then the graph would be decreasing. Right? So if you think about taking a graph, and we've looked at it from the other perspective, or at least some other perspectives in 3.1 and 3.2. If the graph is increasing like this, and I were to draw a tangent line on it, right? My tangent line looks something like this, has a positive slope. So a positive slope correlates to an increasing graph, and a negative slope correlates to a decreasing graph. The third one actually showed up earlier. It showed up as maximums and minimums. Do you remember that in, I think it was 3.1 or 3.2? But it talked about the fact that if you have a derivative that's 0, you have a maximum or minimum. The difference between that on this is that this is saying over the entire interval. So if we have a whole interval for which the derivative is 0, the graph must be constant. Okay? So if I had a slope of a tangent line or a tangent line, and it's like this, then I would have had a 0 slope for the whole thing, right? It's flat. And the graph itself would be this constant line itself, too, a horizontal line. And that brings us to the first derivative test. So the first derivative test says the following. Suppose that f is continuous on the interval and c is a critical number. Now remember, critical numbers happen when we have the derivative. Actually, let me do it this way. equal to 0, or equals to does not exist. Those are critical numbers. Okay? So we have a critical number. So if we have a critical number at C, then if f prime of x is greater than 0 from A to C, and less than 0 from C to B, then we have a local maximum. In other words, it's talking about it changing from increasing to decreasing. So imagine the picture they're talking about. The graph is going from increasing, and then it goes to decreasing. What must be happening right here? Well, it must be reaching a maximum point. Okay? And if we look at part B, or 2 rather, it says if the graph is going from decreasing to increasing, right, the derivative is negative, and then the derivative is positive, what has to be happening at that location? Well, it must have a minimum, a local minimum value. And if it has the same sign on both sides, then it's not one of these. And you might be thinking, okay, but like, don't critical numbers typically have these derivatives of 0? Well, they do, but there are other graphs that do as well. And so let me just give you a real quick example or reminder if I've given it in a previous lesson. If you had the graph of x cubed, this is a really good example where it does something like this as a shape, right? And I actually do have a derivative right here in the middle that's 0. It is flat enough that the derivative is 0 right there. But it's increasing before it and it's increasing after it. So even though I have a critical number there, it doesn't actually end up giving me a local max or min. Okay, so there are cases where that happens. So we're going to do an example to show how all of this plays into us being able to use these pieces of information to find places where it's increasing and decreasing. All right, so our directions say to identify the open intervals on which the function is increasing or decreasing. So we're going to start by taking derivatives. Anytime it's asking you things about increasing, decreasing, maximums, minimums, it's asking for a derivative, and then you're going to evaluate information about the derivative. Okay? So we need to take the derivative, and again, the beautiful thing about Chapter 3 is the derivatives are tend to be much easier to work with than back in Chapter 2. That's a good thing. So, what is the derivative of x? 1. We all like that one. This piece right here, it would be easier for it to be written how?
4x to the negative 1.
Yeah, so let's think of it as 4x to the negative 1. So if I have 4x to the negative 1, what's the derivative of 4x to the negative 1?
Negative 4.
Right, negative 4x to negative 2. And if I were to take this and I were to put it back into a form that's more usable, I would put the x back down in the denominator. So it would look like that. Is that okay? All right. And then what we're wanting to do is we're wanting to set this equal to 0 or does not exist. Now, you might look at that and say, well, it's never equal to 0. And you might be right, depending on the function, and you might be wrong. So this one in particular is kind of hard to just look at it and decide, and the algebra will actually work a little bit easier if we would combine the two pieces into a single fraction. So that's my suggestion at this point, is for us to do that. There's other ways to do it too. You don't have to combine them. You could work with them as they are, but I think it'll be easier for us to see in general if we combine them. So let's actually find a common denominator, which would be x squared, right? And then I'd have x squared minus 4 on top, and I'd have x squared on bottom. Is that all right? Okay, so where is this equal to 0? Well, it's going to be equal to 0 when the numerator equals 0. That is when x squared minus 4 equals 0. And it's going to be equals to does not exist when the denominator, namely x squared, is equal to 0. Right? Numerator equals to 0, the whole thing equals 0. Denominator equals to 0, it doesn't exist. So that's why I kind of like putting it into one piece like this, is because we can isolate the numerator piece equaling to 0 and the denominator piece equaling to 0 to find the two different types of critical points. You can probably look at this and tell me, when does x squared minus 4 equal 0? What x values? 2 and negative 2. Okay? If you're looking at that and you're like, wait a minute, what? Just solve it, right? So especially if it were more complicated, that is what we would do. We would actually move the 4 to the other side. We'd have x squared equals 4, and we'd take the square root. Either way, we get plus or minus 2. Those are two possible critical points, 2 and negative 2. Okay? The other one is easy to solve as well. X squared is equal to 0 when x is equal to 0, right? Okay, so we have 3 critical points, 2 and negative 2 and 0. And here's what we do next. We make what's called a sign chart. So we're going to draw a number line. Our number line is going to include all critical points in order. So negative 2, 0, and 2. Everyone good so far? Okay, so my critical points are creating for me a number line. And what I want to know is I want to know what happens on the intervals, not at the 2, the negative 2, and the 0. I know what happens there. It's either 0 or does not exist. What I want to know is the graph increasing or decreasing there in the intervals, not at the points themselves. So grab a calculator. We haven't done much with the calculator in a while. But we're going to in this section. And I want you to put in the derivative. And it doesn't matter which form of the derivative you use. So if you want to use the first one where I put in 1 minus 4x to the negative 1 or 2, that's fine. If you want to put it at the end where I put x squared minus 4 over x squared, that's fine. Or if you want to do something in between, it's fine too. It doesn't make any difference. Just put it into y1. Okay, does everybody have it in your calculator into a y1 something? Okay, this will be the easiest way to get all of the answers you want at the same time. Okay, so over here on my number line, what I want to do is I want to test values that happen to be in these intervals. So I need a number that comes before negative 2 on the number line, and it doesn't matter what number we pick. So if Colton picks negative 3 and Caden picks negative 7, we're going to get the same answer for what we're looking at in terms of, do I get a positive or a negative? So that's why it doesn't matter. So we get to pick any number before negative 2. So somebody pick me a number before negative 2. Negative 3. Wonderful. I'm just going to write what we're picking above. Now I need a number to pick between negative 2 and 0. Negative 1's a nice choice. I need something to pick between 0 and 2. 1. And then I need something to pick after 2. I'll go with 3. Okay? It doesn't matter what you pick, just pick something that happens to be in that interval. Now, what we want to do is we want to use our calculator and we want to plug those values that I wrote in red into the derivative. And what I care about is, do I get a positive or do I get a negative? So I'm going to go into my table. So if you do second graph, that pulls up the table. If your graph will not let you enter something into it, let me know, and we will change your table setup. Can everybody enter into their calculator if you have it with you today? No. Who said no? I don't. Okay. Anybody else is not allowing them, but none of the number in? Okay, so we're going to put in negative 3, negative 1, 1, and 3. What did I do wrong? My table set up. Oh, that's what's wrong. Okay, mine was actually set up wrong too. Okay, so what did you get in terms of the sign at negative 3? The positive or the negative? Positive? How about at negative 1? How about at positive 1? And at 3? It's positive. Okay, did everybody get those signs showing up for those intervals? Okay, what does that mean? Well, the ones that say positive means that's where it's increasing. And the ones that say negative means that's where it's decreasing. So we're able to write that down. So it's increasing. I'll just start with increasing because it starts on the left. So it starts from negative infinity, and it stops at -2, like this. And it jumps over until I get to the 2, and from 2 on, so from 2 to infinity, it's increasing again. And then it's decreasing in between. I can't just write -2 to 2, though, because at 0, I really have an asymptote, that's what I have at this particular one. So I need to show that it's going from -2 to 0, and then from, 0 to 2 for my intervals. So these are my intervals where it's increasing, decreasing. Now, I didn't ask us for this, but could we also answer the question of where we have maximums and minimums here? We could. If the graph is going from increasing, I'm going to shift my graph down just a little bit so I have a little bit more space to write on top of it. If the graph is going from increasing to decreasing and decreasing to increasing, I have locations where I can identify where I have maxes and mins, right? Didn't ask me for that, but another question might. I could talk about the fact that at x equals -2, as long as it's actually something I can plug in, right? It's not a does not exist value. It's a 0 value, which it is, that I will have a maximum there. And at x equals to 2, I will have a minimum there. Now, that doesn't tell me the point where I have a maximum and a minimum. It only tells me the x value. But could I find the y value? If x is equal to 2, can I figure out what y is supposed to be in this function? Yeah, not with the derivative, right, but with the original function. So I could actually put -2 into my original equation that I was given, and I could figure out what the y coordinate is there. And I could put in the x equals +2, and I could find out what the y coordinate is there. So I could find my maximum and my minimum with this exact same set of information. So being asked to find the maximum and minimum after I've already been asked to find the increasing and decreasing is little to no extra work, right? Very little work. More. I just have to do one extra step, which is to look at the table 2, I guess. To look at the table with these sort of lines that I've drawn in as the increasing and decreasing lines, and then plug that number back into the original equation. It's probably worth noting that because I have 2 decreasing spots, there's nothing happening at 0 here in terms of maxes or minimums. However, even if I had a decreasing and increasing at 0, I wouldn't actually have a max or a min, because if I were to try to plug 0 into the original equation, what would happen? It wouldn't exist, right? And you know what it is. It's an asymptote, right? Because anytime you make the denominator 0, you get an asymptote. So I'm getting an asymptote there is what's actually happening. So even though that the increasing and decreasing could change at that spot, it doesn't necessarily create a max or a minimum. You still have to go back and analyze, well, what did the graph actually do? Did it actually have a value there, or does it have an asymptote there? And a good example of that, and we'll end with this as my good example really quick, I'll just show it over here on the side, is actually the graph 1 over x. So if you were to graph the line 1 over x, you basically know what the graph looks like. It looks like this. This graph is actually 1 over x squared is what I want. It looks like this. This graph is increasing on the left, and it's decreasing on the right, correct? So visually, we can say that this is increasing and this is decreasing. Well, increasing and decreasing would have this sort of basic shape, but I don't have a maximum here. I have an asymptote there. So just because it has the ability to be increasing and decreasing does not necessarily mean there's a maximum. It means there could be a maximum. There also could be an asymptote. Okay? All right, we will stop there for today. We will pick up with example 2 next time.